Okay, so here's our problem. At 1 p.m., ship A is 50 miles east of ship B. If ship B is traveling north at 20 miles per hour and ship A is traveling west at 10 miles per hour, how quickly is the distance between the ships increasing or decreasing at 3 p.m.? So we see we have some directions, north, east, west, and south in this problem. So before we draw a diagram, let's just remind ourselves where these directions are. Generally, we put north at the top of our page, south at the bottom of the page, east to the left, east to the right, and west to the right, to the left. So let's first look at the situation at 1 p.m. At 1 p.m., ship A is 50 miles east of ship B. So ship A is over here to the east of ship B. And they're 50 miles apart. Now let's see what happens. So we're interested in what happens at 3 p.m. Now remember, ship B is going to be going north or upward, and ship A is going west or to the right. So at 3 p.m., which is the time we're interested in, or actually want to know what the situation is for times close to 3 p.m. So when we're close to 3 p.m., our picture is going to look something like this. We'll let P be the position of ship B at noon, and then the actual position of ship B at 3 p.m. we'll call Q, and the position of ship A at 3 p.m. we'll call R. So notice that ship A at 3 p.m. is still to the left or to the right of the point P, because ship A has only been traveling west at 10 miles per hour for 2 hours. So that means it will have gone around 20 miles by the time 3 o'clock comes around. So it's still going to be about 30 miles to the west of or east of where the point P is. So we get a picture like that for what's going on at 3 p.m. And of course, what we want to know is we want to know how quickly the distance between the ships is increasing or decreasing at 3 p.m. Right? It might be increasing, it might be decreasing. It's kind of hard to tell from the information given. So what we want to know is basically how quickly this line, its length is changing. Quickly the length of this line, we'll call it W, is changing at 3 p.m. In particular, what we want to find in this problem. We want to find the rate of change in the length W with respect to time at 3 p.m. That's what we want. So in these related rate problems, there's usually a rate that you want, and there's usually some other rates that are given. So we look at our picture, right? We're thinking about what's going on around 3 p.m. So around 3 p.m., what this line below is getting, below is getting shorter, right? We'll call the length of this line, let's call it X. And so this line is getting shorter. And since ship A is traveling west at 10 miles per hour, we basically can say that we know that that dx dt is equal to negative 10. Of course, the units there will be miles per hour. Of course, you have to use the negative because that length x is getting shorter by 10 miles every hour. So we know how x is changing. We also know another quantity in this problem, which is this line between Q and P. And we'll call the length of that line y. Now the length of that line y, since ship B is traveling north at 20 miles per hour, traveling north at 20 miles per hour, notice that line's getting longer. We know that dy dt is going to be equal to 20 miles per hour. All right, so we have the rate we want, which is based on the rate of W. And the two rates we know are the rate of change of x and the rate of change in y. And now what we need is to have a connection between the variables w, x, and y. So in these problems, there's always something you want, there's something you know, and there's a connection between the thing you want and things you know. So here's the connection between the variables involved. Using the Pythagorean Theorem, we know that the sum of the squares of the two legs of this right triangle, that is a right triangle, since we have north and east, west and south, and all at right angles to each other, we're going to have that x squared plus y squared is equal to w squared by the Pythagorean Theorem. So that's the connection between the variables x, y, and w. And what we need to do in the next step is to take the derivative of both sides of that equation with respect to time, and that'll get us a connection between the actual rates. So let's do that at this point. I'll rewrite the equation. X squared plus y squared equal to w squared. So I take the derivative of both sides with respect to time. Do that, we're basically using implicit differentiation. Remember, x is a function of t, y is a function of t, and w is a function of t. They all change with time, t. So if I think of x as a function of time and use implicit differentiation, I basically get the equation, or I get 2x dx dt plus 2y dy dt equal to 2w dw dt. Now notice we know the values of dx dt and dy dt. Dx dt, remember, was -10. And dy dt was 20. So we can simplify this a little bit to get -20x plus 40y equal to 2w dw dt. And then finally, I can divide both sides by 2w. To get -10x plus 20y, all divided by w, equal to dw dt. So let me rewrite that. This is our expression for the change in w with respect to time. So we get -10x plus 20y, all divided by w. Now remember, our goal in the end is to figure out exactly what dw dt is at 3 p.m. So what's happening at 3 p.m.? According to our formula, we can figure out what dw dt is at 3 p.m. as long as we know what x is at 3 p.m., y is at 3 p.m., and w is at 3 p.m. So let's see what our triangle over here looks like exactly at 3 p.m. So exactly 3 p.m., our triangle looks like this. We have our point P there. Our ship B has been traveling north for 2 hours at 20 miles per hour. So that means we'll have a length of 40 here. All right, so that's our y. So we see that y is equal to 40. And over here, this length will be equal to, the ship B has been traveling west for 2 hours. So this line here is going to be 20 miles shorter than it was at 1 p.m. So we get 50 minus 20, which is equal to 30 for that length. So at this point, we can see that y, we can see that y is equal to 40. And x is equal to 30. Now, of course, we still have to find out what w is equal to. So basically asking ourselves, what's w going to be in this pitch? And of course, we can find w using the Pythagorean Theorem since we have a right triangle here. So we know that 30 squared plus 40 squared is going to be equal to w squared. So we get 900 plus 1600 equal to w squared. That gives me 2500 equal to w squared. Take the square root of both sides. Of course, we just take the positive root since w is a length. And we get w equal to 50. So we now know that w is equal to 50. Now we know w is equal to 50. We know y is equal to 40. We know x is equal to 30. So we can now find dw dt at time 3 o'clock. So I'm going to go to the next page. I'll rewrite the information again. At this point, we're going to find dw dt. Again, we're using the formula dw dt equal to negative 10x plus 20y over w. And of course, at 3 p.m., we know that x is equal to 30, y is equal to 40, w is equal to 50. So we can now do our final computation. So dw dt at 3 p.m. is equal to negative 10 times 30 plus 20 times 40, all divided by 50. So we end up with negative 300 plus 800 on the top. Let's do a 50 on the bottom. So we get 500 divided by 50, which is 10. So the change in W with respect to time at 3 p.m. is positive 10. So we can now state our answer. Okay, since we have a positive 10, that means that this length W in our picture, length W in our picture here, is getting longer. Okay? It's growing with time, becoming longer with time because we have a positive 10. So that means that ship A and ship B are going apart from each other at 10 miles per hour. So the two ships are going apart or away from each other at a rate of 10 miles per hour. In other words, the distance between the ships, in this case, is increasing. They're going apart from each other, going away from each other. And so that's the solution to the problem.